In the previous video, we've talked about the difference between Markov chain and stochastic process. And then we've also talked about the transition probability matrix. And now here in this video, we are going to look at some problems which we are going to try to create the transition probability matrix. So let's start. So let's see the example of gambler's ruin that we've seen before. To summarize the game a little bit, you start with $2 and then you bet $1 at each time step of the game. If you win, you will get this $1 back, and in addition you will get another dollar. But then if you lose with probability 1 minus p, you will lose this $1 that you bet before. You keep playing this game until you reach $4 or you have no money left on your hand, or $0. So to create the probability matrix, first you need to define the possible state at each time of the game. So here the state is the amount of money that you have after you play the game at time t. Okay, so at time 0, obviously your money is $2. And then you don't know for sure the amount of money at each time t, but what you know for sure is that the maximum is that you will have $4, the minimum is you will have $0. So those are the possible states, right? Because after you lose all your money, you cannot play this game again, so you cannot have negative amount of money. The same thing is if you already have $4, you cannot keep playing this game, so you cannot have more than $4 at your hand. And then in between you can have $1, $2, or $3, right? So those are the possible states that you have. And then you see that for the row and the column, the states must be the same. Okay. So now let's fill the probability in this matrix. If you already have lost all your money, so this is your current condition, your next condition is still $0, right? So the probability here is 1, because you cannot play the game anymore. So if you have no money at time t, so at time t plus 1, your status or your state of money is still $0. That's why the probability is 1. And then same thing from t plus 1 to t plus 2, the state or the money that you have on your hand is still $0. That's why the probability is 1. Because once you lose, you cannot play the game anymore. You cannot get any money anymore from this game. Same thing if you already win $4. You cannot play the game anymore, such that the time step t plus 1, t plus 2, t plus 3, t plus 4, and all the time steps after this, for sure you will have $4 on your hand. That's why the probability is also 1 here, and then 0 for all the other amount. Because once you have $4, you cannot play the game anymore. So there's no way you can have $3, $2, or so on. Now at the beginning, you have $2. What is the probability of transitioning from $2 to the other states? From $2, if you win with probability P, you can jump to $3. If you lose with the probability of 1 minus P, the next time step you will have $1. So this is why you have P in this column and then you have 1 minus P in this column. If at one time step you have $1, same thing happen. If you win from 1, you gain $1 to become 2. If you lose, then you will have $0 in the next time step. And then finally for 3, if you have $3, if you win, the next time you will have $4. If you lose, the next time in the game you will have $2. So to read this matrix is that this is your current condition, and then with some probability you will jump to the other state or the other condition in the next time step. We may also use a graph to represent the probability matrix that we just defined in the previous slide. So here, if you already have nothing left in your hand, so the next time step, you still having nothing left in your hand. So the arrow goes from 0, goes back to 0. Same thing if you already win $4, then the arrow goes to $4 and $4 again, because you cannot play the game anymore. But at the beginning you have $2, you have the possibility to go into $3 in one step if you win. You also have the probability of going down to $1 if you lose the game in one step. So this is how to read this graph. It means exactly the same with the matrix. It's just another type of representation. Another example that we've seen before is about choosing balls from an urn. So we start with 2 unpainted balls, and then we pick one ball randomly from the urn, and then we flip the coin. If the coin comes up head, we paint the ball into red. If the coin comes up tails, we paint the ball into black. If we keep playing these games and then we pick already painted balls, we just flip the colors from red to black, from black to red, regardless of the outcome of the coin toss that we do. First, let's define the states. In that problem, the state or the condition that we observe at each time is how many balls that we have for each colors, which is represented by the vector of U, R, B. So the number of unpainted balls, the number of red balls, and the number of black balls. Because we only have 2 balls in the urn, so the possibilities is we have 2 unpainted balls at the beginning, and then maximum we have 2 red balls, maximum we have 2 black balls, and then anything in between. 110, 101, and 011, right? Because there are only 2 balls in the urn, so these are all the possible states. And then, as I've said before, the number of rows must equal to the number of columns, because all the states are exactly the same. Once you've defined the states, you may start fill the probabilities. So let's see if we try to fill the probabilities when we start from the state of 1, 1, 0. So the current state or the current condition is that we have 1 unpainted ball and 1 red ball in the urn. To get the probabilities, we need to list all the possible events starting from this condition. So according to the game, first we pick 1 ball randomly from the urn. So these are all the possible outcomes. You may choose the unpainted ball, you may choose the red ball, right? And then after you choose the ball randomly, you toss the coin. The possible outcomes from the coins are head or tails. That's why I write unpainted twice. I write red also twice, because I want to pair this outcome of the ball that you choose with the outcome of the coin that you toss. So all the possibilities look like this: unpainted and head, unpainted and tail, red and head, red and tail. Once you have listed all the possible events that may occur, both the balls and the coin, now you determine what happened to the ball that you choose. If you pick unpainted ball and the coin comes up head, that unpainted ball will become a red ball, such that your next state will become 0 to 0. right? Because you begin with 1, 1, 0, one unpainted, one red, and then you choose the unpainted, and then the coin comes up head. Now you paint that unpainted ball to become red. So your next state will become 0 unpainted, 2 red ball, and 0 black ball. If you happen to get the coin shows up tail, then you will paint the unpainted ball to become black, such that your next state will become 0, 1, 1. The unpainted ball that you pick now becomes a black ball. For the possibilities or the events, that you pick red ball, the coin doesn't matter. You will paint this red ball to become black. So your next state will become 101 and 101 regardless of the coin. So one unpainted ball because you did not pick that, and then one black ball because you painted black from red. Okay, and then you start computing the probability of all these events. So choosing an unpainted ball, the probability is 1/2 because you have two balls, one unpainted and one red at the beginning, and choosing the unpainted is has the probability of 1/2. And then obtain the coin for showing up head is also 1/2. So the total probability for this event is 1/4. Same here, choosing an unpainted ball from this condition 110 is 1/2, and then the coin shows up tail is also 1/2. So the total probability for this event is 1/4. Choosing a red ball from the initial condition 110, from this initial condition 110 is 1/2, and then the coin showing up head is also 1/2, and then here picking up red ball is also 1/2, and then the coin showing up tail is also 1/2. Once you've listed out all the possible events and the probabilities, now you may put these values into the matrix. So this 1/4 goes to here, right? Because it goes from 110 to 020. Then this 1/4 here goes to this 1/4, and then this 2 because they're ending up in the same state, 101. You may 101. You may sum these two probabilities to become 1/2. So that's how you fill the probabilities. And this is the complete probability matrix. You may pick any value and then you do your own practice to try to obtain the same value as shown in this matrix. Okay, so now here are some questions to check your understanding. I will give you the answer after the pause of the video. So given the probability matrix for the example of the balls in an urn, I say that the sum of a row must be 1. The sum of a column may or may not be 1. We don't really care about it. Is this statement true or false? The answer is true. The sum of the probabilities in a row must be 1 because we need to say that we are currently at one particular state, and then the sum of all possibilities of the states that next we are in must be 1 because those must cover all the possibilities of our state in the next time step. Still on the same example, there's a statement saying that if our current state is 0 to 0, regardless of the coin outcome, we will be in the state of 0, 1, 1 in the next time step. Is this true or false? The answer is true. If we have 2 red balls, then whatever we pick, we must pick a red ball. and then whatever coin outcome that we see, we will paint that ball into black. So that's why the next state will become 0, 1, 1. 0 unpainted, 1 red, and 1 black balls. We will have more examples in the next video, so see you in the next one.